is Joe Clay. I work with Space Design Corporation, and we have a product bundle called Space 3D, and that product bundle contains TSS, Thermal Synthesizer System. As you notice, the presentation title has Thermal Software System, and we've kind of adjusted the TSS into to include a product called Transfer, and that's why the name now is Thermal Software System. In the past, it was TSS, Thermal Synthesizer System. The other part of the Space 3D bundle is SAT, which is satellite or structural analysis tool, and that is another 3D graphical finite element package that focuses on structural analysis. So again, I'm Joseph Clay. I go by Joe. My email is joe.clay@spacedesign.com. Uh, and the name of the company is a contraction of the word spacecraft design, and so we're space design. And our website is www.spacedesign.com. Okay, and so that was a bit of an introduction, and the just the background information about TSS, and this is in the TFAWS agenda. Thermal Software System, TSS, is a thermal analysis tool to model spacecraft in the space thermal environment. The software converts CAD-based models, specifically IGES or STEP, to a thermal engineer friendly format. Analysis can be performed to determine radiation conductors, conduction network, the conduction and capacitance network, and produce temperatures with a 3D graphical environment, something that I think in today's world most thermal engineers are familiar with. The software is built on C++, Microsoft.NET framework. We actually have now Microsoft 4.8. The previous version of Microsoft.NET in around May timeframe was actually discontinued, and we upgraded the software to use 4.8, which is still supported by Microsoft. And we also have OpenGL 3D graphics, solid rendered 3D graphics, and all of this is really done in-house. So we don't have, say, a third party that does our graphics or that does the graphical libraries, other than those kind of low-level OpenGL, .NET, and C++. Okay, and so we have Space Design Syndifluent. We are a manufacturer of Syndifluent. It's called Space Design Syndifluent, which is a numerical integrator for thermal and two-phase fluid models used to solve for temperatures and fluid flow. So in this presentation, I'm going to discuss enhancements in TSS version 16 and more, and something that Joe Lepore, our support personnel, pointed out in the presentation, that there's a couple things that are from the past, but I'll point out why I include them in this. Okay, so trying to move something around on my screen here, so maybe I can see more. There we go. So I kind of already explained what thermal synthesizer is. Thermal synthesizer system. It's a commercially available software package. It was originally manufactured by Johnson Space Center. We commercialized it in 1998. The latest version is version 16, which is available on Windows 10 and Windows 11. In the past, we've done we improved the databases for the faster analysis for the James Webb Space Telescope. And I'm also going to talk about some of the new exciting developments with version 17. Since I moved my mouse, I'm not moving the screen. Okay. So here's a very short list of the things that are in version 16. We added elliptical cylinders. So that's one of the shape types. We added a parabolic cylinder, which is like a sheet, a hyperbolic cylinder, which is another type of sheet. And I'll show an image on the next slide. We improved the GUI. My example, and this is what Joe Lepore was pointing out, was that the dockable toolbar is actually in version 15. And the reason I'm bringing it up is we made kind of a WinCommon library. We grouped a lot of things within the software together. We included step in transfer, which really we had that in the past, but we've been doing a lot of work on getting the CAD models through step into TSS. We added G4Trans Space Design Syndifluent version 6.0b. In the past, we had Intel, and we still do. We still support Intel Fortran, but now we also have G Fortran. Uh, and then there's, which is a free version of Fortran. We added 32 character submodel names. We have RCD data and DA11MCP calls for the some additional things into Syntafluent. We have high precision output and faster graphics. And then just recently, we released a new version. 16.03 was kind of combined into the Microsoft.NET 4.8 release. We added millimeters as units, and that's because a lot of CAD models are in millimeter units. And we also have a very simple enhancement node outline configuration to change the node outlines on your models, just to make it look a little bit more distinct in some situations. So here's a slide. We show that we've added the surface types, the elliptical cylinder down below, parabolic cylinder, hyperbolic cylinder up above, and they're on the right-hand side of the surface list there, shown in yellow. And these are new radiation and conduction surfaces that you can use in your models, in addition to all the other surfaces that you see there, the rectangle, trapezoid, disc, ellipse, triangle. I'm reading the things off the right-hand side there. There's a polygon, cylinder, cone, sphere, elliptical, cylinder, I believe. There is a ogive, torus, box, paraboloid and ellipsoid, and below the yellow line there is quadrilateral, a B-spline surface, and then there's of course, the things in the yellow box. And below that there's solids. There's the solid brick, solid cylinder, solid sphere, tetrahedron, a wedge, and a non-orthogonal brick. So those are the different surface types we have in TSS. And in version 17, we've extended that to the pyramid, and we'll show that at the very end of this. So there's another solid. Okay, and again, just to point out, Joe Lepore says we have this in version 15, and he's 100% correct. But my point of showing this is that this is now moved into more of a common library that we have in our software. So in the previous slide, you saw that there was the surface icons, and I read through the list of those. In this image, you see the exact same geometry in the background, but I right-clicked. I did the setup pull down, and I did hide object buttons, and so it just expands the view a little bit more. And then I right-click on the toolbar, and I can add show tools, show surfaces, show solids, show CAD, show group, and then all the things are on a nice tool strip or toolbar at the top there in the yellow box. Okay, one other thing that we added into version 16, and we actually rolled this out in a late version 15, but we really claim it was supposed to be in 16, but it worked so well that we ended up rolling it out early. So there is G-Fortran support for space design Syntafluent version 6.0b. We have here some comparisons of thermal analysis or runs that we did with the Intel Fortran and the G-Fortran, and we show the timing. And the first thing is just a generic thruster model that was the old TSS class model. And you can see that that took about 26.15 seconds in Intel Fortran, and it took 22.64 seconds in G-Fortran. So if G-Fortran took slightly longer, it's free. Intel, is a cost. You have to pay for that. And then the ISS model, which is traditionally the EVA thermal model that is used, that uses TSS. It took 85.3 seconds in Intel Fortran, and it took 89.79 seconds in G-Fortran. And so it actually runs faster in the free G-Fortran version. And then there is a run of the JWST model. The Intel Fortran took 2,587 seconds, and the G-Fortran took 2,413 seconds. And that looks like G-Fortran is faster. if I'm reading the numbers correctly. I think that's anyway. So it's slightly faster to run in G4 Another thing we have in the Space Design Syndifluent 6.0 B is 32 character submodels. And this is actually throughout TSS. We added the ability to have longer submodels so you can have a much more detailed reference to submodel names throughout TSS. An example, you can do this in geometry. You can have a rectangle that's in a submodel, and in concap that's in that submodel. That's a very long name. And so again, this is added to the Syndifluent for a header. So your header data cards would have a long submodel name. There's also RCD data, which I talk about a little bit here in a couple slides. Or actually, I'm sorry, not in this. There was a different presentation, not in this presentation. RCD data, which allows you to have, it records points of interest to the end user. So instead of just doing the old D data, which captured a certain time step, it would actually look for inflection points and things like that to record for the end user. There's also, we added for more or less sensitivity analysis, DA11MCP calls. Most people using Syndifluent are familiar with DA11MC call. That adds a heating rate, but it assigns it to a node and from an array. And in our case, we set up a function now that does plus. So you can have a series of DA11MCP calls. So you can have solar, albedo, and Earth IR, for instance, as separate values. And what we've done is did some advanced orbital mechanics that I talk about near the end of this presentation. And the advanced orbital mechanics has different sources so that we can have an additional set of sources that are added to the Syndifluent. Okay, and this is very simple, but to the output of from say RADK, we added the air so that your output now records the air, and you can have a value that you can see in your actual Syndifluent file what the air value was. And this is all part of our sensitivity analysis that we're working on. Okay, and another thing that we have is we have faster OpenGL graphics. We released these faster graphics in the version 16.01 Rev A on September 16, 2021. And just to showcase this, that we added millimeters, this is just one location where we have millimeters. This is the transfer application. And so we can have input of millimeter units and then output of millimeter units into TSS. And so all the way throughout TSS, all the applications now support millimeters. Another thing, and I'm just showing this model because this is the Say Cheese model that's a CAD model that has many different holes drilled through it and different sections taken out. And sometimes in the graphics that we have, there'll be shine through. So you'll kind of see some of these holes shine through. And that's with the node outline width equal to 1 and the node outline offset equal to 0.6. And what I show here is we're capable now of changing this to 1.5 and 0 so that oftentimes models will look better. And that's why there's no shine through in this image here. And we released version 16.03, revision B of TSS, on June 6, 2022, which was just, a couple months ago. Okay, now I'm going to switch gears a little bit and talk about some of the enhancements that are kind of coming in the future. These haven't all been released, or they're nearing release, I guess, is kind of where we're at with some of them, and some of them are a little bit more still in the works. And the one that's kind of already been released is the Space Design Syndifluent modified Dufort-Frankel method. We actually have Dufort that's currently in our Synda, that's in our version 16.03 release. But we're still kind of improving it, so that's why I included it in the version 17 list. So in the transfer application, these are the list of enhancements for version 17. In the transfer application, we have further step development, and I'll go into some of the detail on that. We also have thermal surfaces with Booleans. We have advanced orbital mechanics, so we have multi-body dynamics. We have space design Syndifluent is adding the modified Dufort-Frankel method. We also have the forward back and the forward transient analysis. And modified Dufort-Frankel is a transient analysis. Extended capabilities, we're adding pyramids, and we're also working on advanced contact conduction. And that's a little bit obscure right now. We're still trying to get that thing going, the advanced contact conduction. Okay, so in this step, we're doing additional things. As an example, well, let me just give you the goal of the transfer step development is to move complete data from a CAD package via the standard for exchange of product model data, or STEP. And STEP is the acronym for standard for exchange of product model data. In the past, we used to do things like, we still do this, advanced BREP, closed shell, and advanced face. And they're actually hierarchical there, the way that I show them. You'd have to have an advanced BREP, and then a closed shell is referenced, and then an advanced face is referenced to the closed shell. Working with FreeCAD, we found that a lot of models that were written out had some additional step entities, and so we've implemented the geometrically bounded surface shape representation, the geometric set, curve bounded surface, and then there's another higher type that's a composite curve segment, and there's outer boundary curve and boundary curve. Another thing that we're working on is, in a sense, to have one of the main focuses on transfer is to take surfaces and create thermal surfaces. And here I have an example of the basic way of creating thermal surfaces. So we have the CAD surface in blue on the left, and this is the transfer application. On the left is a step model, and we're only showing really one object in the step model. And then on the right is the transfer geometry model. So you can see both things at the same time and move your data from your CAD step file over into TSS. And you can do that interactively. And so here we have what we've done, and we said, do thermal surfaces and break down rectangles with holes in them into triangles. And so in the past, we would have, it ends up being faceted. We also have the concept of Booleans, and we're working on this to implement conduction so that we get the proper conductors. So when we do the Boolean now for the transfer, in a sense, what we do is we remove the Booleans to get the thermal surfaces, then we reapply the Booleans to the thermal surfaces. And so you see now we get the correct geometry. And so our goal is, once we move this into concap, that our conductors and our capacitance values would be correct, because we'll move the edges back for the triangles, and we use a weighted Ka over L value. In one of the past TFAWS, we presented this methodology of how to do this. But so you would have this rectangle, and then on the inside, let's say if there was a cylinder there, you could break that down in an 8 by 8 even division in the circumferential direction, and then make direct connections with the thermal model. Okay, another thing that we have been working on is advanced orbital mechanics. Just to give you the current orbital mechanics that are in TSS, we have planetary basic, planetary Keplerian, date dependent, sun referenced, heliocentric, planetary surface, and trajectory. So, and based on these mathematics, the ones that are actual orbits, not the trajectory or the planetary surface, the resulting orbit shape is strictly an ellipse, a parabola, or a hyperbola. And you can also have a circle, which is a simple ellipse. Used for many thermal analyses, these past orbital mechanics. One example is the International Space Station, the US EVA thermal model shown here, which is used for EVA thermal analysis. You can see the flux cubes that are around the station and the places that the astronauts can do spacewalks. The temperatures are mapped onto the surfaces. And you can see the scale there is shown from 284 degrees Fahrenheit to negative 460 degrees Fahrenheit. Okay, and what we did for this is we implemented the Yoshida integrator, and we also implemented a command set. So there's a mathematical component that was used to solve multi-body orbital mechanics, and actually multi-body trajectories. A command set n-body has been added to call the Yoshida fourth order solution and input the necessary conditions to run the simulation. Uh, as an example, we made a halo loop around L2. Here's a list of some of the parameters that went into the model. There was the number one value, or the number one object is Earth, the number two was Moon, the number three is the halo sat, and then we solved the multi-body dynamics using these parameters. And I'm sorry, I don't know how my screen just jumped there. I didn't move it forward. The sample of n-body, here's a sample of n-body commands. N-body count 3, which sets the number of bodies to 3. We can have a max of 1,000, but it does take quite a bit of time to solve many, many bodies. You want to be careful how many objects you have in the model. And then n-body run starts the analysis, and you can say, set the end time and things like that. Okay, and so here is an image that we have plotted using the Yoshida integrator. We ran a test case where we have a halo orbit, and so on the right-hand side is the location of the Earth, and there's a line that's the vector from Earth to the Moon out to L2. And the satellite orbits in that kind of arc on the left-hand side, and then on the right-hand side is another image of that. The satellite starts at the bottom and then goes around in a halo loop 2 times. And this is visualized in a rotating, you can say oscillating or pulsating reference frame. And the points, each one of these points is plotted every 20,000 seconds or 5.56 hours. And so you can see the orbital mechanics. I'm sorry, I claim that I didn't change slides. It just automatically did that. I don't quite know why it's moving. But so here is, we modeled a CubeSat, and we show here the CubeSat for a lumped capacitance. The temperatures as it went throughout that entire orbit, the lowest is negative 16 degrees Celsius, and the highest is about 6 degrees Celsius. And you can see the periodic as it goes around the halo loop. Okay, and I kind of already mentioned this, but in version 17, there is the early release of the Dufort transient solver. The modified Dufort-Frankel method is a forward difference approximation using a Taylor series expansion. It can be called in the space design send to fluent header operations data, and the call is Dufort. Another thing that we're working on right now are pyramids, so that we have a way of connecting 3-point based objects to 4-point based objects. A good example is if you want to go from large non-orthogonal bricks to smaller non-orthogonal bricks, there's a method you can connect these pyramids to tetrahedrons in a combination that'll get you from large blocks to small blocks, and that's why we're implementing these. We're implementing these in TSS and in SAT so that we have kind of a continuity between all of our applications. Uh, the there's 2 pyramids here shown, and the thing is at the bottom there's a 4-point surface. It's a solid. There's a 4-point surface at the bottom, and then you can see the 3-point triangles on the top of both solids. And on the far right, you can see the solids. There's the pyramid added below the tetrahedron. Okay, and the last thing, and this is something that we're just kind of starting on, is the advanced contact conduction. Some of our CONCAP conduction methodology is a bit dated, And so we're going to update that to allow people to do connections that are not just based on the endpoint of the conductor stub. Here, the way that we do this, we have tolerance spheres. And so if things are within tolerance, and there's nothing wrong with this method, we're not going to get rid of this method. We're going to keep this method, but we're going to add on top of this to have an augmented type method or a more advanced contact conduction methodology. And so the first thing, just to show here, if you wanted to make this connection, these spheres would not connect because, well, there's only two that would really connect, and that's kind of in the center. As you can see my mouse here, these two might connect. But what we really want to do in this case, we're really just thinking is that we want to connect these two, these three in a certain way so that we have this conductor connected to this conductor here, and in addition connected to this one. And there's a methodology in TSS to do this by using an arithmetic node so that we can connect multiple conductor stubs. But what we want to do is in the future have it so that we would use the edge length, so that here we have this edge and this edge, and we would end up making this K over L to each one of these based on the intersection of, say, a cylinder or whatever the contour is at the edge. And so that we have an easier way of making, a more intuitive way of making conduction connections in CONCAP. So that's the end of my presentation. I do have a movie to play if anybody is interested in the advanced orbital mechanics. But I'll open it up for any questions. Not quite sure if I go to the chat. Is either Eric or Eric, are you there?
Yes, I'm here.
Okay. Are there any questions at this time? I don't see any.
Yeah. Yeah. Any questions? Thank you, Joe. Excellent presentation. If you have any questions, please go type them in the chat. Let's see. Well, it looks like we don't have any questions.
Okay.
Go ahead, Joe.
Well, I was thinking I could play the previous presentation that is on our advanced orbital mechanics and describes how we did the halo
Oh,
loop.
yeah.
Now, and I
Would
don't
love to see
know,
that.
we have time. Okay.
Yeah, we have
Let
time.
me,
See that.
okay, let me go. And so there's a bit of a repeat, not much, but there's a bit of a repeat. So let me go, I guess I gotta go with share. I hope I have it open. I may have to go. I may have to stop sharing for a second and go find it. So can you give me just a second,
Yep. Yep.
Eric? Okay, hold on just a second.
Okay.
I feel like we should have some kind of music. Sorry, I apologize. This is going to take a few
Oh,
seconds here.
well, anybody on the line wants to sing?
Yeah, yeah.
Not me, though.
Hello, my name is Joe Clay. I work for an aerospace and
Okay,
software company in Houston, Texas.
okay. And
Okay.
Eric, can you hear that?
I hear some audio. Yep. Heard some
Okay,
audio.
I'm gonna share that. It's really loud on this side, but I don't know.
Okay.
Is it all right on your side? I mean,
Yeah, actually, it's a little soft on my
oh,
side, so
okay,
we'll
okay. Hold
see.
on. Then let me share that then.
Okay.
Uh, share movies. Okay, and can you see it now?
Yep. See it.
space design. Presenting our software tools.
Okay, the little, can you turn it up?
Mechanics that models multiple body dynamics in the cislunar space.
Even louder.
Presentation.
Probably as loud as you can get it.
That seems like as loud as I can get. I don't know if you can see,
Okay.
but I turned it up to 100%.
Oh, okay.
What's weird is on this side, it seems really loud.
Space 3D, TSS, Advanced Orbital Mechanics for cislunar. Matt Clay is in Austin, Texas, where he did the mathematical program. Joe Lepore is in Richmond, Texas, where he did the thermal analysis and testing. We have been in business since 1998. Company name is a contraction of spacecraft design. Space 3D Thermal Synthesizer
Okay,
System,
that's perfect.
often referred to by its acronym TSS, is a commercially available software package for spacecraft thermal design, analysis, and control. The software features OpenGL solid rendered graphics and Microsoft .NET user interface. Space Design Syndifluent is a powerful solver for thermal and fluid combined solutions that was used to reduce temperatures at the end of our presentation. The current software version is v16 and is available for Windows 10 and Windows 11. Version 15 is currently being used by most of our customers and had database improvements that allowed faster analysis for spacecraft like the James Webb Space Telescope. We have some exciting new development to share that is being implemented in version 17, Advanced Orbital Mechanics. Before we discuss the development of Advanced Orbital Mechanics, let's discuss the current orbital mechanics capabilities of the existing software. TSS has 7 current orbit types that for the most part are based on Keplerian mathematics, resulting in an orbit shape strictly a circle, ellipse, parabola, or hyperbola. One additional orbit type is an Earth trajectory that is specified by latitude, longitude, and altitude. And the final orbit type is planetary surface, defined so the craft is in an inertial position on the planet's surface, moving at the planet's rotation rate. These types of orbits are used to perform many thermal analyses. One example is the extravehicular activity, EVA, thermal analysis for the International Space Station. Shown here is a temperature map on the ISS with heating calculated using the planetary basic orbit type. The specific orbit used had an altitude of 260 miles at a beta angle of 0 degrees. The basic orbit type is circular and good for specifying worst case hot and cold cases by utilizing the beta angle. The beta angle of 0 degrees, this is the coldest cold case heating. Temperature range is from 284.37 degrees Fahrenheit to absolute zero. For EVA, temperatures external to the structure are determined using flux cubes that you can see distributed at locations where a spacewalking astronaut can move. Our goal for advanced orbital mechanics is to extend our current Keplerian-based simulation environment to the cislunar environment that often requires non-Keplerian multi-body orbital mechanics. An example of a non-Keplerian trajectory is a halo loop around the L2 Lagrangian point. To accurately visualize a loop like this, it is necessary to utilize a rotating, pulsating reference frame. Reference frame is based or centered on an Earth-Moon L2 vector, shown here drawn from the Earth to the Moon and beyond to the L2 point. Points calculated for the spacecraft in 3 space during the multi-body simulation are transformed to produce an accurate picture of the halo loop. As the view of the Moon rotates around the Earth, we transform the rotated points back to a singular reference frame. Additionally, the Moon's orbital eccentricity moves it in and out relative to the Earth in a pulsating fashion. Also account for this during the transformation by scaling the distance to the Moon in the mapped reference frame. The result is a Moon that remains stationary in our rotating, pulsating reference frame. To model the non-Keplerian trajectories, we implemented the multi-body Yoshida fourth order algorithm in our orbit application. The Yoshida integrator method is a highly efficient solver that can model Lyarzú trajectories including halo loops. As a demonstration of our Yoshida implementation, we chose to model a three-body problem with the Earth, Moon, and satellite in a halo loop around the L2 Lagrangian point. We started with a calculated best guess starting position and iterated until we achieved a stable halo loop. We chose an L2 halo. The Yoshida multi-body solution should work for L1 loops and trajectories between the two loops. We are presenting a snapshot of our development where the Yoshida integrator works, but some of the process flow and analysis are limited. Ongoing development is improving these two limitations. In the end, we want to combine our existing thermal capabilities of TSS to determine heating, temperatures, and provide trajectory visualization even better than those displayed in this presentation. In the pursuit of our development goal, we have implemented a command set to call the solution and input the necessary conditions to run the multi-body simulation. Here are some of the parameters to produce our halo loop around L2. Shown are the mass of the Earth, Moon, and halo satellite, along with the initial state vectors for position and velocity. Masses are in kilograms, positions are in meters, and the velocities are in meters per second. We also ran a simulation with a more massive 2,000 kilogram satellite and got identical results for the halo loop as those seen with CubeSat. The mass of the spacecraft has no measurable effect on the much more massive Earth and Moon. As an example of the n-body command set implemented in our orbit application, we have n-body underscore count that sets the number of bodies and n-body underscore run that starts the Yoshida simulation. Our simulation has a limit of 1,000 bodies. The more bodies used, the longer the analysis time. Using the n-body command set and the Yoshida integrator, we produced a halo loop around L2, shown here at two different angles. Both images use the rotating pulsating reference frame to show the spacecraft trajectory. The top image has the vector between Earth, Moon, and L2. As seen from this view, the halo appears as a crescent. The lower right image shows a view looking down the Earth-Moon vector with the Moon at the center. The initial spacecraft starting point is at the bottom of the oval, and the spacecraft moves in a clockwise direction. This halo loop is referred to as a northern halo. Although the points are plotted every 20,000 seconds, 5.56 hours, the solution time step is much smaller. To show a dynamic visualization of the halo loop, we have a short movie that displays the satellite motion viewed from the rotating pulsating reference frame. It's centrally located in the image. The time is displayed below the moon in seconds. The total duration is 28.5 days, and the satellite makes a loop every 15 days. The movie shows the motion twice. The first run through shows an individual position for the satellite, and the second run through leaves previous positions on so the full loop can be seen. After the second run through, the remaining image is the same as that shown on the previous slide at the lower right. To quickly get thermal results, remember our software is geared towards Keplerian orbits. We used our animation application to move the spacecraft in relation to the moon, while our orbit application was used to move the Earth relative to the sun. The moon orbiting the Earth used a Keplerian orbit type. The moon's distance from the Earth has a minimum of 354,000 kilometers and a maximum of 403 3,000 kilometers. A diffuse source emitted from a divided sphere surface, the size of the moon, acted as the moon IR. In this image, the sun is to the right, with the hot side of the moon always pointing towards the sun. The spacecraft is located at the axis system shown. Each axis location has the z-axis pointing away from the Earth, parallel to the Earth-Moon L2 vector. 28.16-day moon orbit around the Earth has 30 points to calculate heating. The Earth is located at the center of this image, and the moon is rotated around the Earth 360 degrees, with each point being displayed. The counter-rotating moon has an angular velocity of 0.5326 degrees per hour. The moon is tidally locked to the Earth, meaning one side of the moon always faces the Earth. But to get thermal results quickly, we set up a counter-rotating moon diffuse source. The source has 4 temperature zones, and the hot side always faces the sun. The following short movie shows the diffuse source that is not tidally locked. Our test spacecraft was something simple, so we could focus on the non-Keplerian orbital mechanics, but we felt it necessary to show temperatures to give a fundamental feel for the calculated heating. The test craft was a 1U CubeSat with cubic dimensions of 10 centimeters by 10 centimeters by 10 centimeters. The cube optical properties were gallium arsenide solar panels with a solar alpha of 0.9 and an IR epsilon of 0.83. The total mass of the cube was 1.3 kilograms, and we used the capacitance of 6061 aluminum. The minus z axis of the cube was pointing toward the moon, parallel to the Earth-Moon vector. The halo loop duration was about 15 days. The oval shape is nearly an ellipse with a 75,000 kilometer semi-major axis and a 58,000 kilometer semi-minor axis. Before we get to the temperature response, we want to show the maximum incident heating per source, and the spacecraft side, the maximum is incident on. Shown here is an energy balance equation on the lumped mass spacecraft. On the left side, we have the capacitance, represented by the mass and specific heat of the entire satellite, times the temperature response over time, represented by dt divided by d tau. The right side of the equation shows the radiation to space in the first term and a series of subsequent terms representing different absorbed heating. The first Q is solar heating from the sun. The next value is the Earth IR from the Earth emitting at its temperature. Earth solar albedo, that is the sun reflected from the Earth, moon IR from the moon, and finally a value for moon solar albedo, that is the sun reflected off the moon. The direct incident values are independent of optical properties, and their magnitude depend on the 10 centimeter by 10 centimeter CubeSat surface area. Solar has a maximum of 13.49 watts and is much larger than any other incident heating. Earth albedo and Earth IR are comparable in magnitude. Both are close to 3/4 of a milliwatt. The moon IR value is a little over 12 milliwatts, and the moon albedo is 9/10 of a milliwatt. The moon albedo is still under development, but since we know the location of the probable maximum, we made a circular Keplerian orbit that represented the location of the spacecraft relative to the moon to get a value. Using the heating value shown, we solved for temperature using Space Design Syndafluent and got the following temperature response. The minimum temperature is -16 Celsius and the maximum temperature is 6 Celsius. Over the 28-day lunar orbit of the Earth, where 2 halo loops of 15 days occur, the spacecraft experiences 4 periodic increases and decreases. To show the temperature dependence on moon IR, we ran our solver without moon IR and would double the moon IR value. The lump mass temperatures are dominated by the solar absorbed. Temperature change is on the order of 0.1 Celsius, showing for a lumped mass, the heating values other than solar have little effect on temperature. Note that the scale changed in our plotting software since the final value is now slightly below negative 16 Celsius for the case with no moon IR. We have shown our advanced orbital mechanics work by demonstrating a spacecraft heating and temperature response in a Earth-Moon L2 Lagrangian point halo loop. The solution technique for the non-Keplerian orbital mechanics is Yoshida fourth order integrated. For the CubeSat, in a halo loop, the temperature range is negative 16 to 6 Celsius and showed little dependence in temperature from sources other than solar. We are continuing our work by implementing solutions to the Lizazou trajectories using Linstead-Poincaré method with differential correction to determine halo loop starting locations without iteration. We are also implementing moon albedo without requiring Keplerian orbits. Finally, improving the interaction between applications so the process flow of thermal analysis is more streamlined. Thank you for listening. Are there any questions?
Okay, Eric, are you there still?
Yep, I'm here. We have any questions?
Still no questions. Is there anything
Okay.
we can do to get a question?
All right. Well, great work. And can you talk a little bit about? I noticed the James Webb Telescope. You had that listed. Was this the software that they used for
Yes.
James Webb?
So I believe on the it's, and again, we're kind of always a little bit on the outside, but it's the manufacturer of the satellite did use our software. We did some improvements so that they could run it faster to the databases, and we saw a huge improvement in the speed to calculate the radiation conductors and the heating rates. I mean, we do have models that we've seen from them, so we know that they used it. And we also believe that the kind of the oversight at NASA had the software to run those models too. Um, uh, and I don't want to go into a lot of detail because I don't. You never know how much you're supposed to say or not say.
Right. Right.
It's a NASA project, so I'll just leave it at that. I mean, they were very. I believe that they were very happy with uh, the software capabilities at the time when they did the James Webb. And they thanked us. I mean, for the work that we had done.
Well, that's great. That's exciting. A big accomplishment. So, well, thanks. Excuse me. Thank you, Joe. I appreciate you presenting. It was a great
Okay.
presentation. And
that concludes the presentation. Then
yeah.
thank you, Eric, for having us. And I want to thank the programmers at Space Design that do all the work, the hard work, of implementing the software. So, and the support person, Joe Lepore.
Yeah. Yeah. I was just watching your presentation and just thinking how amazing that is and how much work goes into that. So, yeah, I concur with that.
A lot of stuff, a lot of mathematics, and a lot of programming.
Yeah. Okay. All right. Well, thanks everybody, and we'll see everybody after lunch.
Bye.